I like to continue with this other very important paradigm, so-called self-learning networks or competitive networks. In this case, there is no target value, only the data, only input data, and kind of miracle, but this network can somehow classify, can make groups. Let me mention why. Because if we are lucky, and if we have a real-life data samples, usually there is some kind of statistical correlation between the elements. And this network can figure out the statistics. They will figure out the statistical occurrence of the different elements in it automatically. Instead of telling that what groups are there, they will classify. They will produce classes. This is the most simple example. That's what I like to show you. Even it is old, very old metaphor, easy to understand. This is what I like to show you at the beginning now. As I mentioned to you, there are three major elements to understand any neural networks. First is how the processor works. It is very simple. It has an activation function. This is the activation, the S, summing the inputs multiplied by the weights. The output is here, but is a function of this activation. In this case, this is how the activation looks like, the transfer function. It is a linear, meaning that the S is at the output. Output is equal to S, the sum. And then the S is calculated by input multiplied by the weight and summing from all of the inputs. Clear? This is how the processor works. In most cases, this is how the artificial neural network works. This is how the processor is. And then the second is the topology, how to connect the elements. This competitive network based on a single trainable layered network. As you see, it is two-layered. One is an input layer like this, but in this time, these inputs are not modifiable, meaning that there is no learning inside. Learning happens only here, only these weights. It is a feed-forward network, and then there are some limitations for this network, but at least we can understand how it can work. For example, the very basic expectation here, the sum of the weights equals to 1. So all of the weights, one weight, another one, so on, all together it is 1. If one is larger, another should be smaller to achieve this one sum. The second, each weight values, of course, between this range, between 0 and 1. Should be, because I cannot achieve this first requirement. And then another limitation for this specific network is that input is binary, meaning that it can 0 or 1 at the beginning. And this is how it works, because the third step is the learning. First is the neuron, second is the topology, and the third one is the learning, how to adjust the weights. Because the goal is here also to do some useful work, some kind of classification, without providing expected outputs. This is how it works. First, we can set the initial weights. In a simple case, it is random. We agreed it is between this range, between 0 and 1. And we need to be careful because the sum should be 1. It can be no different. Then, if we will provide one specific input for the network, we can calculate the output vector of it. Plugging all of the inputs to the weights, multiplying with the weights, we will calculate the outputs for all of them. And then, if we are calculated for all of the outputs, then we can select the big ones, the biggest one. We can check somehow which one is the biggest one. And this is the key here. If we select the biggest ones, we will name it as a winner. Because only this output, the biggest output, will have a chance to be able to change it. The way I will change it to be able to increase this potential to have a winner again. So we select the winner and changing the weights only for the winner. For example, stepping back one here. If this is the winner here, we will change only these weights. This one, this one, this one, and this one. Not changing anything to the other ones. Doing this, we will let the network to be able to achieve the same result even better in next time, because that will be a winner again. because we are increasing those weights proper to the input vector. Clear? Because of that, we need to do it in a cycles, continuously, selecting the winners always, and modifying only the winners' weights, and then eventually it will classify without providing output expectations. Interesting enough. Here is the algorithm, easy to follow. First, setting the initial weights, calculating the output vector, selection the highest values according to the winner-takes-all principle, setting it to 1, and then all of the others not changing. And this is how we'll adjust the weights. We will calculate the output and then divide it by m, meaning that how many inputs are 1, because we don't want to change, we cannot increase it more than 1, so we need to somehow, the modification should be less than 1. This is the way to do it. The outputs divided by the number of 1 inputs, and then we will repeat it as long as we can do it, till then no change will happen. So this is how it will work eventually. For example, these are the first stages, and this is the outputs. Gradually, it is decreases, but in this point it will increase, and finally this will be the winner. This is also a cyclic procedure. We need to do it in a cycles, but eventually it will classify. It will find the statistical elements into the data set. Interesting. It is called self-organizing. They organize itself using this very simple method. There is another somehow related area, very typical in real neural networks, so-called the competition using lateral inhibition, meaning that this is the topology of the network, meaning that this is connected to the other ones. This one is connected to this one and that one. If this is high, it will somehow repress this other two what is next to it, because the winner will somehow suppress the next one next to it. This is called lateral inhibition. Based on this method, we can achieve this kind of function. We can detect edges with this. The edge detection, it is something very important. As you will see in a convolution network soon, the feature detection one is the key element these days. How to detect features. One of the basic features is the edges. To find the edges, where are those? Something like this. One of the very early self-organizing network was the so-called Kohonen network. The reason why I bring it here, not because it has a big importance these days, it doesn't have. But it has a very important lesson what we can learn from it, meaning that this guy, Kohonen, who was a Finnish person, he didn't care what was in the US. He didn't care what kind of support he can get for the research. His aim was to make some kind of typewriter, what can be utilized to dictate for it. Having a microphone and tell the words and it will type the letters. Excuse me? Don't understand. Please. Oh, I'm sorry. Yes, I'm sorry for it. Yes, this is the topology. Sorry. Thank you. I will change it. So, clear, it is a topology. Single-layered feed-forward, fully connected network. It utilizes somehow the same concept what I learned in a previous network, the winner-takes-all method. But instead of having single elements in it, the neighbors are connected. The close neighbors are connected. That's why it can name it as a cellular network, because some kind of cells in it. Based on this method, he was able to produce a very interesting and successful solution way back in the 80s, in 1980s. He made this so-called phonetic typewriter, having a microphone, telling the Finnish words, and it was able to type down the letters. These days, it is not a big task, because we can dictate. We can have many dozens of programs that we can utilize to dictate. That's why there is a discussion, we should learn to write in the future or not. There are some schools in abroad when they stopped teaching handwriting. they can type. But maybe in the future type is not needed also because we can just dictate. And this was one of the very first solutions for this problem. And the reason why I brought it here to show you what was his method to do that. First, he utilized this very specific neural network, somehow learning the phonemes in the speech, the elements of the speech. Based on these phonemes, he utilized a special rule base. If such and such phoneme is in a speech, this is how we can write it. What is the character to write it down? Shocking enough, he used thousands of rules based on his knowledge, his linguistic knowledge. And then, using these rules, he was able to use a word processor and type it down the characters, way back in the 1980s. And then he achieved 97 and maximum 97% of accuracy. It was pretty good. We are close these days also, but it was 40 years ago. And one of the core elements was here this neural network. And he also utilized analog methods. For example, he utilized filters first to cut down the value underneath 5 kilohertz. And then he utilized the 12-bit analog digital converter because it had to be processed digitally. And he utilized the sampling, digital sampling. And based on these samples, he utilized this fast Fourier transformator to transform it from time domain to digital domain, discrete domain. And based on these discrete values, he was able to use this neural network. And then it provided the proper phonemes. Based on this phoneme, he was able to produce the given character. It looks extremely complicated, but when he started this process, it was almost hopeless to do that. But finally, he was able to do it, long time ago, 40 years ago. And this is the training algorithm, very basic, what I like to show you. Instead of get lost inside, I just like to tell you how it works. It is the neurons are connected to next door neighbors. We will provide the input data, those fast Fourier, the output of these fast Fourier transformers, and then we will select the winner one and change the environment in the winner ones. And then provide the next one, the next character, select the winner again, and change not only that one to the environment for the close elements also. And doing that step by step gradually, and eventually this network was able to calculate and figure out the phonemes. Based on these phonemes, it was able to use the rules, and the rules provided the proper letter to type in a typewriter. So because of that, you can follow it. I don't ask in a test. This will be not in a test. I just want to show as an example. It was such a successful and complicated method way back, using this complicated technology. And then there are some equations also. I don't want to ask you in a test those equations, don't worry. The reason why I brought it here because I like to show you it was also math behind that, not just a heuristic way to change the weights. There was some way to calculate it exactly. Based on these calculations, he was able to do something really useful. One of the interesting features of this Kohonen network was to be able to use as a visualization device. For example, this is also a result of my students here in the school a long time ago. If you provided two inputs, one input and another input, and this input was generated from some two-dimensional object. For example, like this. We got samples from this two-dimensional subject. We provide it to the network, and based on these previous complicated methods, what I just showed you on a slide, it was able to somehow represent on a surface this two-dimensional object. We was able to see it. We had just data, x1 and x2, and providing this x1, x2 into the network, eventually was able to see it on a screen. It was a visualization device, fantastic, very good. One of the most shocking result what we got from this result, if we provided this kind of input data, not two-dimensional, three-dimensional data, not just x1 and x2, x3 too. And then the object what we used for this training was, for example, this cylinder, this kind of cylinder. getting data from the surface of this cylinder. And providing this to this Kohonen network, we was able to see the cylinder on a surface like this. Not just cylinder, we was able to see a ball also. And if we omitted one part of the cylinder or the ball, we was able to see it on a surface. And this is one of the lessons what I learned from this one. Neural network can do not just only classification, it can do visualization too. That's why it is a part of the data science, because we have a huge amount of, vast amount of data, you need to be able to see it, to understand. And this can be one method to use it. To use some kind of neural network-based visualization, we can see like this here. Something like that. Even if there was a serpentine on the surface of this cube, we was able to see like that. Instead of just having a bunch of data in an Excel file, but is not visible for us, we don't have a brain to understand that thing. But using this, we can see it on a surface in 2 dimensions. It was fascinating. The next thing what I like to cover very briefly, that the brain, a very important lesson, the brain is not a universal device. One of the most important lessons what I teach you here, what I tell you here, using artificial neural networks, we cannot make a so-called Turing machine that can solve any problem. It cannot. It can solve a specific problem. The specific problem what was designed for. The good news somehow related to this, we have a huge broad range of different problem groups. And if you have a specific kind of network, it can solve that kind of problem group, not just one single definite problem. That kind of group, for example, classification, or calculate time series, or calculate something else. It is designed specifically for that purpose. And then, and if you understand how the real brain works, we can have a clue, some kind of metaphor to build it in a network, in an artificial way. Sometimes it is not easy to do that. We are in the middle of this process. As I mentioned at the first class, there are 2 major goals studying artificial intelligence. First, to make smart machines, to make something useful machines, what is more efficient than we are. As we know, the so-called weak AI, it is already here. We can make extremely useful applications in many areas what can surpass our capabilities. It can much better than us. Calculations, for example, or translation or something like that. It can be much better. We can make a long list. I already did in the first class. And we are just at the beginning. Because if you want to make a good technical device, great help if you understand how the nature does the same thing. And good thing we are surrounded with many intelligent creatures. I share the idea with those people who said not only the human is intelligent, the creatures around us, even the very small one, can be extremely intelligent, solving some very particular problem very efficiently, sometimes better than us, if the person is specified for that specific task, to avoid chemicals or avoid light or something like that. Even having an extremely, relatively simple structure inside. And if we understand how this structure works, then we can build it, test it, and since it is usually very robust, these applications are very robust, we can use it, even don't understand all of the details in it. We can make a very useful, practical device, still working, and if it's stuck somehow, we will try it again. And this is the situation what we have. And as the whole topic will progress in the future, we will have more and more detailed knowledge how to build a specific network, and that specific network will do a specific job extremely efficiently, much better than us. For example, one of the most popular things these days is the so-called convolution network. Extremely complicated if you look in it. Can be viewed as a simple way. You can understand the basics if you like, but if you want to go in the real details, it can be extremely overwhelmingly complicated. For example, just one idea to see how it works. There is an input pattern here, some photo, and we want to have a class here to tell what is that, what kind of photo, what is on a photo. And to be able to do that, we need to do this kind of layers, 1, 2, 3, 4, 5, so many layers in it. And each layer has some kind of logic, why we have that logic, that layer. We could have a good explanation, not easy to do it. But good news, it is not a dream, it is reality. There are dozens of, maybe thousands of people on Earth who can do it efficiently. The big companies are focusing on that. Tesla, for example. They are using this convolution network for guiding cars. Yes?
Is the logic of these layers created by humans? So like, is it hard-coded or is it created via fuzzy algorithms?
It is created by neural networks usually, the short answer. We can hard-code it. We will show you I will show you a very hard-coded version to understand it easily. But the good news is that we can do it automatically. So we can do these layers automatically using training, providing data. That's why we need to have a huge amount of data. And this is the explanation why these days we have a successful neural network application. We have a huge amount of data. Second, we have a huge computation power. Parallel computers built into our little devices. And we have a network. We can utilize the network. And all of the big companies, Google and Facebook and others, are using a vast, huge data centers. And those parallel computers can be utilized for calculating neural networks. Fantastic. So, looking into this topic, I wanted to find something for you what is useful. And instead of just selecting randomly, I selected one of them and looked it up. I said, great. If you're interested, you can see it. I will show you what is that. For example, this here, this very simple explanation, I will go there right away. It shows if you want to classify, for example, this creature here, to recognize the panda bear. What can be a complicated procedure, but a simple example here. First, we need to figure out the elements of this photo. And to be able to do that, the researchers use the metaphor of what is in a brain. Because what is our understanding, the human cortex, visual cortex, is some kind of layered situation. We have visual cortex 17, 18, and 19, these layers. Numbered it, because one of the guy who analyzed this brain structures numbered it. That's why we have this so-called Brodmann numbers on a brain, when a structure is similar within that layer. The question was, what is the purpose of this layer structure? We know the answer for that. It can select the features of the picture, what we see. It can select the angles, it can select some elements of the pictures, and based on these specific selections, we can put together these elements, so-called features, the nose and the ear and so on, and based on that we can make a classification. We can recognize objects even if it is upside down. We learn it was there, and it is showed up there, we can still recognize it, because those key elements, the eyes and the ears, are in the same minute. To be able to do that, this is, for example, this convolution network is made for. And let me go there, let me show you what is that. I will go to the thing here. And I upload, after this class, this literature also for you. If you're interested, you can take a look. First, you see the backpropagation. There's a basic introduction for neural networks, and here are the convolution networks explanations. Here, let me see you. Let me see this here.
Like unusual numbers with this filter, this minus.
Let's go back to the beginning, just to see some part of it.
Want to pass your certification exams first time?
Which is divided by 9, because there are total 9 numbers. Handwritten digit 9. I will give you a very simple explanation of convolutional neural networks without using much mathematics, so that even a high school student can understand it easily. Let's say you want the computer to recognize the handwritten digit 9. The way computer looks at this is as a grid of numbers. Here I'm using -1 and 1. In reality, it will use RGB numbers from 0 to 255. The issue with this presentation is that this is too much hard-coded. If we have a little shift in digit 9, for example, 9 here was in the middle, but in this case it is in the left, and the representation of numbers just changes. It doesn't match with our original number grid, and computer will not be able to recognize that this is number 9. There could be a variation since it is a handwritten digit. There could be variation in how you write it, which will change the two-dimensional representation of numbers, and again you will not be able to match it with the original grid. So we use artificial neural network for this kind of case to handle the variety. In this deep learning series, we have already looked at artificial neural network video on handwritten digits recognition. If you have not seen that video, please make sure you see it so that your fundamentals on artificial neural networks are clear. In that, we created a one-dimensional array by flattening the two-dimensional representation of our handwritten digit number. And then we build a neural network with one hidden layer and output layer. And this dense neural network will work okay for a simple image like handwritten digit. But when you have a bigger image, let's say this little cute looking koala, the image size is 1920 by 1080. We have 3 as RGB channel here, one for red, green and blue. In this case, the first layer neuron itself will be 6 million. If you have a second layer with 4 million neurons, you're talking about 24 million weights to be calculated just between the input and hidden layer. And remember, deep neural networks have many hidden layers. So this can go easily into like 500 million or 1 billion of weights that you have to compute. And
this is one of the reasons, what I think it is clear for you, why 40, 50 years ago there was no way to do efficient neural network applications. Because to calculate this amount of weights, there was just no way, these old-fashioned computers. Even if we are using some kind of compression method that you will learn soon, it was hopeless. Now we had to have this very powerful, these computers, what we have.
That's too much computation for your little computer. See, my rabbits are getting electrical shock because it's just too much to do. So the disadvantages of using ANN or artificial neural network for image classification is too much computation. It also treats local pixels same as pixels far apart. If you have koala's face in a left corner versus right corner, it is still a koala. Doesn't matter where the face is located. So the image recognition task is centered around the locality. Okay. So if the pixels are moved around, it should still be able to detect the object in an image. But with ANN, it's hard. So how does human recognize this image so easily? So let's go into the neuroscience a little bit and try to see how we as humans recognize any image so easily. When we look at koala's image, we look at the little features like these round eyes, this black prominent flat nose, this fluffy ears, and we detect these features one by one. In our brain, there are different set of neurons working on these different features, and they are firing. They are saying, yeah, I found koala's ears. Yes, I found koala's nose, and so on. Then these neurons are connected to another set of neurons which will aggregate the results. It will say if in the image you are seeing koala's eye, nose and ears, it means there is a koala's face in the image. Similarly, if there is koala's hands and legs, it means there is koala's body. And there are different set of neurons which are connected to these neurons which will again aggregate the results saying that If the image has koala's head and body, it means it is koala's image. Same thing with handwritten digit 9. There are these little edges which come together and form a loopy circle pattern, which is kind of like a head of digit 9. In the middle you have vertical line, at the bottom you have diagonal line. Sometimes you don't have diagonal line at all, but we know that whenever there is a loopy circle pattern at the top, vertical line in the middle, diagonal line in the end, that means digit 9. So how can we make computers to recognize these tiny features? We use the concept of filter. In case of 9, we have 3 filters. The first one is the head, which is a loopy circle pattern. In the middle you have vertical line. In the end you have diagonal filter. So we take our original image and we will apply a convolution operation or a filter operation. So here I have a loopy circle pattern or a head filter. This filter right here. The way convolution operation works is you take 3 by 3 grid from your original image and multiply individual numbers with this filter. So this -1 is multiplied with this one is multiplied with this one, and so on. In the end you get a result, and then you find the average, which is divided by 9 because there are total 9 numbers. And whatever number you get, you put it here. Now this particular thing is called a feature map. So by doing this convolution operation, you are creating a feature map. So you do it for the second round of 3 by 3 grid. Here I am taking a stride of 1. You can take a stride of 2 or 3. Also, you don't need to have 3 by 3 filter. You can have 4 by 4 or 5 by 5 filter. And then you keep on doing this for your entire number. And in the end, what you get is called a feature map. Now the benefit here is wherever you see number 1 or a number that is close to 1, it means you have a loopy circle pattern. So this is detecting a feature. In the case of koala, this will be eye or nose, because for koala, eye, nose, ears are the features. So by applying loopy pattern detector, I got this one here in my feature map. I also call it the feature is activated, it got activated here. For number 6, it will be activated in the bottom in this area. If you have 2 loopy patterns, the feature will be activated at top and bottom. If you have a number like this, it might be activated in different area. In summary, when you apply this filter or a convolution operation, you are generating a feature map that has that particular feature detected. So in a way, filters are nothing but the feature detectors. For koala's case, you can have eye detector, and when you apply convolution operation, in the result, see, you got these 2 eyes at this location. If the eyes are at a different location, it will still detect because you are moving the filter throughout the image. And they are location invariant, which means it doesn't matter where the eyes are in the image, these filters will detect those eyes and it will activate those particular regions. Here I have 6 eyes from 3 different koalas and they are activated accordingly. Hooray! The hand of koala is in this particular region, therefore when I apply hands detector, it will activate here. Now for number 9, and I'm just moving between number 9 and koala so that the presentation is simple enough and you still get an idea. In case of 9, we saw that we need to apply 3 filters: the head, the middle part and the tail. And when you apply those, you get 3 feature maps. So I applied 3 filters, I got 3 feature maps. And this is how these feature maps are represented if you are reading any online article or a book. They are kind of stacked together and they almost form a 3D volume. In case of koala, my eye, nose and ear filters will produce 3 different feature maps and I can apply convolution operation again. And let's say this time the filter is to detect head. By the way, the filter doesn't have to be 2D. It can be 3-dimensional as well. So just imagine this first dimension is representing eyes and the second slice is representing nose and third slice is representing ears. And by doing that filter, you can say that koala's head is in this particular region of an image. So you are aggregating these results using a different filter for head, and now this becomes a koala head detector. Similarly, there could be koala body detector, and now we got these 2 new feature maps where this feature map is saying that koala's head is at this location and koala's body is at this particular location. Then we flatten these numbers. See, in the end, these are like 2-dimensional numbers. So we can flatten them. So convert 2D array into 1D array. And then when you get these 2 arrays, just join them together. After you join, you can make a fully connected dense neural network for your classification. Now, why do we need this fully connected network here? Well, you can have a different image of koala. See, my koala is sleeping, he's tired. So now his eyes and ears are at a different location. Look at his ears. See, they are here. For previous image, the ears were in a different location. So that generates a different type of flattened array here. And you all know, if you know basics about neural network, that neural networks are used to handle the variety in your inputs such that it can classify those variety of inputs in a generic way. Here the first part where we use convolution operation is feature extraction part. And the second portion where we are using dense neural network is called classification. Because the first part is detecting all the features, ears, nose, eyes, head and body, etc. And the second part is responsible for classification. We also perform a ReLU operation. So
let me stop here for a second. I hope it is interesting for you. You can take a look, you can watch it at home if you like. And what is a point, what I like to make here, based on this step-by-step procedure, we can build a very useful neural network application to recognize things. So we, for example, this so-called convolution network usually utilized in pattern recognition areas, because it can detect features just like we can do. Our brain is specified for detect different edges, different elements in a picture, regardless of the position. Based on these detectors, we are able to recognize complicated things. This so-called convolution network mimics this method, extremely useful. Let me show you here. This is the basic concept. First, we have the so-called feature detectors, and then the next step is here. Somehow shrink the size of the network. It is called the polling. Somehow cut it shorter. If you're interested, I hope you do, you can finish this video. The guy will explain to you what this polling is, how it works. You can understand very easily step by step. And then we can do some kind of transformation on the transfer function, the activation function. It is called relative linear unit. Instead of using this exponential function, you are using some kind of some kind of limited linear function to make it easier to calculate. And based on that, we can do a polling again to shrink the size of the network, cut it down smaller, and then we will use the classification using the backpropagation, just what we learned. This is the way how it works. Fascinating. And The convolution, as we agreed, as we learned, this is a feature detection. It's a complicated word. Convolution it's a bad word. This is convoluted. Our brain is convoluted, somehow mixed up and banded, something like that. Not easy to understand. One way to explain convolution is not easy to understand. Using this very simple example, we can understand the steps of it. And as a result, can provide some real-life good application. And then first thing is the filter, meaning that doing the convolution. And then, based on this feature mapping, we can somehow shrink the size of the network, and then we can classify it using a regular classifier. This is the basic steps of the convolution networks. First, this is the convolution. These are the main characteristics of the network. This is the relative linear unit method, somehow make it easier to calculate. And then finally doing the polling to shrink the size of the network to make it easier to execute. These are the elements of the convolution network. It is one of the most often used method in these days in pattern recognition. If you're interested, the first literature what I showed you, this very simple explanation, but there are two courses what I already pointed last time. It is in the literature, but you can look at up if you like. Finishing this course today, I'd like to summarize very briefly what is here. First, we understand already. First, we need to collect training data, and then we need to design a problem-specific neural network. It should be problem-specific. Let me mention, not a general computer like Turing computer, Neumann computer. It is a very specific one for specific tasks. Then setting the initial weight and network parameters, transfer function, layers, numbers, processors in each layer. What is not easy to do that, kind of black art. And then we need to set the target performance, when we can stop it, and then we need to select the test procedure, how to test it, and then we need to do the training and testing as long as it is okay. If not, yeah, we have a bad luck. But usually it is a successful thing, and it makes better result whatever other method did before. Why it is beneficial to use neural networks? This is what I'd like to conclude today. When we can collect representative training data, there's a good chance to use neural networks. Then, if we don't have equation, then also we're good to have a neural network. If we have equation, let me emphasize this. If we have equation, we already know how it works. Use the equation. This is the most efficient way to do it. Don't do this neural network training. Use the equation, plug the data in it, and then calculate it, and that's it. But in most cases, in real-life situation, we don't have equation. We have data, vast amounts of data. And this is the case, we can use neural networks. And if the training data is not complete, noisy, there are some partial good data, we can still use neural networks. Because we don't have rules, don't have equations, we can use a training, and the training shouldn't be 100%, it can be 99.something%. Even it is 97, sometimes very good. 5% error is not a problem. We can make 5% error always. Then if we have many related inputs and output data, this is the typical case for neural networks. Because it is a kind of black box. It is not black inside because we see already what is inside. This kind of convolution, this kind of filtering and parsing and so on, interesting elements of it. And since it is our profession, we can handle it. If we invest enough time in it, you can have a good knowledge, and it is a very marketable knowledge for the close future. Thank you for your attention. And next time, when I will see you a week from now, I'm going to cover the basic sensors. How does it work? And I'd like to tell you what lesson we can learn from nature and how we can utilize it in technology. Thank you very much for your time.